Moon Science, a deeper look at Jupiter's moon and our own. You're listening to Are We There Yet?, the radio show exploring space exploration. Hi, I'm Brendan Byrne. Far away from Earth, an icy moon called Europa orbits Jupiter, and scientists think that there could be signs of life hidden somewhere beneath its surface. And a mission is heading there right now to answer that age-old question: could there be life outside our own planet? We'll speak with Paul Byrne of Washington University in St. Louis about Europa, its potential for life, and how scientists might find it. Then, we're looking at the conditions on our own moon, and a mission is studying the lunar environment for radiation. We'll speak with Johns Hopkins University Applied Physics Laboratory's Drew Turner about selene and how it can help in future lunar missions. That's ahead on Are We There Yet? Millions of miles from our planet, scientists are on the hunt for life. Europa is an icy moon that orbits Jupiter. It's slightly smaller than our own moon, with an ocean underneath its surface. Within those waters is where scientists think they may find habitable conditions, or even signs that life existed there. That's what Europa Clipper is going to try and find out. The probe will reach Europa in 2030, hoping to observe and find answers to the question of whether or not there could be life outside our own planet. But before it even gets there, scientists are investigating the potential for life, both in the past and present. Here to talk more about Europa is Paul Byrne. He's a planetary scientist at Washington University in St. Louis. Paul, welcome back to Are We There Yet?
Thank you, Brendan. Lovely to be back.
Hey, it's good to have you again. It's always fun to talk about Europa. We've got a spacecraft heading there now, but scientists like yourself are still kind of studying the moon before we even get there. What is the latest in what we know about Europa?
Europa is a fascinating place. And the reason it commands such attention and interest, like not just within the science community, but the public at large, is because we think it may have the ingredients that are required for life as we know it. Liquid water, organic chemistry, and some kind of energy source. And Europa seems to tick all those boxes. We know, or we strongly suspect, that it has a big, deep ocean underneath this outer icy shell. We think there's good evidence. In fact, we now know from lots of different measurements that there are organic compounds on the surface of the moon, and so it seems likely that there are compounds inside it. And it also, we think, experiences a process we call tidal heating, which is basically where you get a big tide between, in this case, Jupiter, the planet it orbits, and the moon surrounding it. And this tidal heating slightly kind of gently kneads the interior, perhaps generating at least enough heat to stop that global ocean from freezing. On paper, Europa looks to be a very encouraging place where we might find evidence for extant or certainly extinct alien life. And so that's one of the reasons why people have been spending decades looking to try and get a way to study it before we have spacecraft there, like our recent study, for example, just thinking about what we might find when we get there, what kind of questions we should ask.
Let's talk about that recent study, Paul, because you looked at what could be happening on the ocean floor of Europa. What did you find?
So we know that on Earth, there are many places in the seafloor, deep underwater, where there are thriving life communities. And the life there, unlike most life that we're familiar with, which on the land or the sky or even in the shallow ocean, is dependent on sunlight for what we call photosynthesis. There are ecosystems deep underwater where it's so dark that sunlight never gets there that undergo what's called chemosynthesis. So they use chemicals to generate the nutrients they need for life. And we know these processes happen on Earth because in the 70s, we discovered these so-called black smoker and white smoker hydrothermal vents. And upon the discovery of these vents, which we really didn't expect, it opened up this whole, literally, figuratively, world of where you might find life that isn't necessarily going to be on the surface. And like I say, in the case of Europa, where we strongly suspect there's a subsurface ocean, it stands to reason that where that ocean ends in the bottom is going to be rock. And so for a long time, people have thought about the possibility that there might be these kinds of hydrothermal systems that exist, perhaps similar to Earth or perhaps different. And so we wanted to think about what, if they were there, what would it take for them to be sustained, say, over geological time, and therefore potentially sustaining an ecosystem. And so we don't have any direct measurements of the ocean floor. We expect that it's there. But for us to really get down into it, we would have to send something through the ice shell into the ocean. And we are optimistically many decades from that technology. So this is a theoretical study. But what we're able to do is we're able to assume some things, I think reasonably. We assume it has an ocean floor. We assume that that ocean floor is probably going to be made of rock, and we have a pretty good understanding of how rock behaves. And so we can make these assumptions about what kind of rock it is. And essentially we did two things. We figured out first what kind of strength that rock has. Because what we know in these hydrothermal systems on Earth, that often, not exclusively, but often they're sustained by fractures in the rock. And if you've ever driven past a road cut or a quarry, or you've just seen rocks anywhere out in a hike, you know that rocks always have fractures in them. That's just a common thing rocks have. When we have these fractures, water is able to percolate through these fractures and react with rock. And it's that chemical reaction between rock and the water that actually generates these nutrients. And so the first thing we wanted to figure out is, well, how likely strong is the seafloor? How likely fractured is it? What would that mean if it weren't fractured, or if it were very heavily fractured through other processes that we might consider? And then the second thing is to think about what processes essentially are present today. So our study focuses on modern Europa, and there's a reason for that I'll come back to in a moment. And we basically wanted to know what would happen if you have these phenomena like things like these tides or other geological processes that can either make a fracture or cause a fracture to move, either of which would allow water to percolate down and potentially reach fresh, unreacted rock, because that's the process that essentially sustains these ecosystems on Earth. And what we found was that, at least for the kinds of hydrothermal systems with which we're familiar on Earth, it seems unlikely that even the strongest tides, for example, or really any other phenomenon we could think of, would be able to generate new fractures enough that over millions to billions of years, you could keep that water percolating through the ocean floor. So that doesn't mean that there aren't places where you have these hydrothermal systems. And there are other hydrothermal systems they're kind of quieter, they're not as energetic. Those things might still be there. But what we find is that geologically, there's probably not a lot happening on Europa's ocean floor today, which means if there is going to be some kind of life ecosystem there, it's going to have to be reliant on processes that aren't quite the same as what we know on Earth. We're not ruling out life. We can't rule out life on Europa. What we can say is that the processes that certainly we recognize on Earth are probably not operating.
You're listening to Are We There Yet? The radio show exploring space exploration. I'm Brendan Byrne. We're speaking with Paul Byrne, planetary scientist at Washington University in St. Louis, about Jupiter's moon Europa and if life is possible on this icy world. Paul, the paper and what you've just described shows us that there probably isn't the ingredients for life on the ocean floor of Europa. Why is that a good thing? Why did you publish that anyways?
So here's what drives me. I have a really interesting, I find it fascinating to think about where life could be today and in the past. And so what we're beginning to learn is that you can see different parts of the solar system might have been more or less habitable at different times. And actually, this feeds into a big question we have for Earth. How is it that Earth seems to have been able to certainly host life? It doesn't mean that it had life, but it has capable of hosting life for almost the entire planet's history. And that has huge implications for things like exoplanets and what we might find or expect to find orbiting other stars. So the way I see this Europa study is that it's putting another brick in this construct of our understanding of what makes a habitable environment and how you keep it there. So even if, and again, we cannot rule in or out life on Europa today, not without, in my opinion, truly getting onto the surface and into the ocean, which is, like I say, technically challenging, to say optimistically. Doable, but years ahead of us. But even if we found that there were no life in Europa today, for example, that doesn't mean that there wasn't there originally. And even if we find that there was nothing there originally, that's still a really important data point, because it tells us, well, maybe these aren't the conditions that we need for life, or maybe these environments aren't as potentially habitable or as encouraging as we once thought they were. And that's still going to be useful for us to understand where we should be looking and where we should be considering we should be looking for life. Maybe that is the deep subsurface of Mars. Maybe it is in the clouds of Venus, or maybe it's in some other condition that we don't see preserved in the solar system today, but we might discover around other stars. So in my view, all of this is important toward that journey we have, which is to try to understand ultimately, not just are we alone, but how and why are we alone, or are we not?
Paul, you mentioned that the work that you did in this particular paper and some of the other work that you do, it's a theoretical study, right? Where you don't have direct evidence of any of these things because we cannot get, a rover to the seafloor of Europa. But I've got to imagine, and you've alluded to this just a bit here, that what you are uncovering through thinking of what is happening on these planetary bodies is going to drive what questions you ask when we do get to directly measure them, like when Europa Clipper is there. Is that what's happening here?
Any information we get is going to be better than what we have right now because we have, relatively speaking, so little. And that's one of the driving rationales for the Europa Clipper mission. So NASA launched this mission a couple of years ago, October 2024. And Clipper is a remarkable mission. It's exceedingly capable. This thing is now, I checked this morning, it's about 205 million miles from Earth, which is just crazy. It's not going to get to the Jupiter system until 2030, but in that time, it will be doing various flybys. It's already done a flyby of Mars. It'll do a flyby of Earth later this year. And it does these flybys of the inner solar system to essentially accelerate itself and get the so-called gravity assists, and then off it goes through the asteroid belt out to Jupiter. But Clipper is, there have been plans to develop and build a mission dedicated to look at Europa for decades. And it was the work of a huge number of people to really make this thing work and launch the mission and equip it with the most advanced instruments that we could possibly put on this thing. My view for Europa, and I think a lot of people in the Europa Clipper mission will say this, is that the astrobiology component, the potential for discovering either extant or extinct alien life, is enormous. It's huge. It's exciting for Europa. But let's say these future missions ultimately show us that Europa is dead as a doornail. That doesn't mean it's not an important or exciting place to continue exploring. So Clipper is going to definitely give us new information, very important information on the potential astrobiological potential of Europa. But it's also going to give us core information as to how these kinds of worlds form. Europa in a geological sense is every bit a planet as anything else in the solar system. We don't call it that because it's orbiting a bigger planet, but it has geological processes. It has this outer surface of ice, which itself is very complicated. And we've recently detected things like ammonia on the surface, which suggests that we do have that organic chemistry present. It has a subsurface ocean. There's more water in Europa and more liquid water than any liquid water on Earth by several times, which is to say that anytime in a movie when aliens come to suck Earth's ocean water up into their spaceship, that's kind of dumb because you could, for much less energy, just go to the Jovian system or even actually the Kuiper Belt. Anyway, but the point is that it's a fascinating world. We should be exploring all of these worlds.
Tell those aliens to go suck water from somewhere else. I like that. Paul, I mean, at this point, you lay out this just incredible world that Europa is, and that little factoid that it has more water than Earth is pretty wild. When you start getting data back beginning in 2030, will you be more surprised if you don't see any evidence of life, whether current or past?
I don't know, but I can tell you with absolute certainty that I am going to see stuff that's surprising. Every time we've ever sent a spacecraft anywhere, we have been surprised by what it's returned. And I think what that tells us is that we should be open-minded and expect the unexpected. And for example, Clipper is going to give us an unprecedented images of the surface at a scale that we just do not have right now. The only other mission that's really gone up close to Europa before is NASA's Galileo mission, which operated in the late 90s and early 2000s. We're going to get unprecedented images. We're going to get unprecedented measurements of the chemistry of the surface. Potentially, we'll see evidence for plumes, which are these features that we think may be present based on Hubble Space Telescope observations. We'll also get really, really impressively good data for what the interior structure and gravity field of Europa looks like. And the reason that's important is because that's the kind of measurement that we would use to refine our models. And it might also, depending on how low Clipper can get, and maybe potentially for an extended mission, which is where NASA would continue operating the spacecraft beyond its planned original mission, it's possible that we would eventually get data that might tell us whether we could even detect features on the ocean floor or not if they're there.
We've been speaking with Paul Byrne, planetary scientist at Washington University in St. Louis. Paul, thank you so much for joining us.
Always a pleasure. Thank you.
Still to come, a closer look at our moon's environment.
We do hope that this data set can be used to develop better engineering models that can be used to ensure lower risk and better safety for future lunar surface missions.
Studying lunar radiation. That's ahead on Are We There Yet? You're listening to Are We There Yet? From Central Florida Public Media. I'm Brendan Byrne. Soon, a crew of 4 will blast off on a mission around the moon and back. It's a big step for human space exploration, but what will the crew actually be doing on the trip? the science of Artemis 2. That's next week on Are We There Yet? But for now, we're talking about a different moon mission, Selene. This mission is a part of NASA's Commercial Lunar Payload Services, or CLPS, and it will study radiation on the moon. It's only about the size of a microwave, but the payload packs a scientific punch, and its research will help humans and robots on future missions to the lunar surface. Here to talk more about Selene and why it's so important to know about moon radiation is Drew Turner. He's a research scientist at the Applied Physics Laboratory at Johns Hopkins University. Drew, welcome to Are We There Yet?
Thanks, Brendan.
So we're going to talk about Selene. This is a really interesting mission that is heading to the moon, and we'll talk about that whole process in a moment, but this is going to study radiation on the moon. And I want to ask you, Drew, how much do we actually know about this right now?
We have understanding going back to the Apollo era from some of the measurements that they took during that time. And since then, we've had some orbital measurements and a few from the lunar surface, including a Chinese mission that just went up a little while ago. But currently, our best understanding of the entire environment is from these models that we have, which basically take a look at cosmic ray inputs and then how those cosmic rays are creating this secondary radiation environment from the lunar surface itself as those energetic particles from space interact with the lunar surface materials and create these showers of secondary radiation. But there's never been a ground truth measurement of the comprehensive incident radiation coming in from space and then the comprehensive secondary radiation right there at the surface.
You're talking about ground radiation on the surface of the moon. That sounds terrifying if you were somebody who was going to be walking on the moon, right?
Yeah,
I mean, why is it important to understand how much radiation there is and how it behaves?
Yeah, so the key thing here is those models that I just alluded to, they are kind of conclusively stating that the radiation dose, so the dose equivalent in electronics as well as human bodies, that is the ionizing radiation, the stuff that is dangerous to us as well as electronics, that radiation dose is actually worse on the lunar surface because of this secondary radiation than if those electronics or that human would just be in free space getting hit by cosmic rays from all sides. And it's for that reason that it's really important that we go up and actually experimentally prove that, right? Or test that hypothesis. And that's precisely what we want to do with Selene.
Is this going to help with human missions, robotic missions? What will be the kind of advantages of knowing this, getting these measurements from the ground?
It's ultimately a science mission, right? So we're going up to test this hypothesis that we have from these models. The ambition, though, or the goal here is that that science data set, once we analyze it, once it's on the ground and we analyze it here, will be useful for future missions and any kind of operations on the lunar surface. We do hope that this data set can be used to develop better engineering models that can be used to ensure lower risk and better safety for future lunar surface missions.
I got to ask, because I'm terrified when you say radiation and on the surface. Why does the Earth have the same thing? Does it get pelted by solar radiation and it holds it?
That is a fantastic question. So yes, indeed, Earth is being bombarded by cosmic radiation as well. And by cosmic radiation, I mean solar energetic particles, right? So cosmic radiation coming from the sun itself, our own star, anomalous cosmic rays, which are coming from the heliosphere, so kind of like our star's bubble in space, in interstellar space. And then also galactic cosmic rays and extragalactic cosmic rays. So those coming from elsewhere in the galaxy and even beyond. That radiation is hitting Earth and the Earth system. The trick is there are distinct differences between Earth and the moon. The first and main one being the atmosphere, right? So the presence of the atmosphere. That is a pretty effective shield layer in itself because it's just a lot of material that stands between us on the ground and space. So what we get in terms of cosmic radiation that's hitting us right now, and you and I are both being hit about once per second kind of thing with our bodies right now by secondary particles from cosmic rays that have scattered down through the atmosphere. And you get these kind of showers of radiation that come down. But that atmosphere is a really good shield. It's a nice layer. Above and beyond that, you've also got the magnetic field of the planet, which also serves as a shield, at least at the lower energy range of these cosmic rays. And combined, those are two things, the atmosphere and the magnetic field, the magnetosphere, that the moon just doesn't have, right? It's an airless body with no magnetic field. So when you're on the surface, you're exposed to the pure throes of space above you.
So we're getting pelted by much smaller amounts every few seconds, but small enough where we don't get superpowers, right? I mean, we don't have to worry about this. Okay.
I mean, unless there's some theories that say that small amounts of radiation are actually good for evolutionary processes. That has yet to be proven, but maybe that is our superpower, right?
All right, I'm gonna bask in those cosmic radiation rays that are hitting me. So thanks for that, Drew. Let's talk about how Selene is actually going to measure this. Tell me a bit about the spacecraft and the mission.
So the spacecraft we're going up on is unknown currently. So we're part of the Commercial Lunar Payload Services program under NASA, so CLPS. And what we're providing is hosted payload that will go on to a future commercial lander on the moon. And our payload consists of an energetic particle telescope with 2 apertures, one looking up at the cosmic radiation coming down onto the surface and one looking down at the secondary radiation environment coming off the surface. That's called CRISP. And then also a fast neutron sensor that we're calling FAST, which is actually looking at the neutron secondary environment, right? So the neutral part. The telescope's looking at charged particles. The neutron one is looking at neutrals.
And how big is this whole kind of operation? It's 2 instruments, right? Will it be on one kind of rover bus or something like that?
It'll be mounted to the lander, whatever lander we get. And the whole thing is about the size of a microwave, entire thing, right? So that's both instruments and our digital processing unit, electronics box. That all interfaces to the lander via an aluminum plate, right? That we will custom tailor for the lander that we get.
Very cool. We've talked about CLPS on this program before, and it's such an interesting program that allows for science payloads to get to the moon. I'm wondering how it works. Did NASA come to you and say, hey, we want to measure this kind of solar radiation on the lunar surface? Or did you pitch them and say, hey, I've got this idea, we need to measure this, and it's probably going to be helpful for you in the future?
So it's a good question. So we proposed Selene to an opportunity that was solicited by NASA, right? We were one of many that proposed, and we were one of 3 that was ultimately selected.
It really is a new era of exploration, right? That scientists like yourself are able to put payloads on the moon, and there have been a handful that have already gone, right?
Yep, exactly. This new program is really exciting, right? It's opening up all sorts of new avenues to getting to the lunar surface and doing a bunch of different science there. Like we're doing this combination of planetary science, looking at how the surface processes are affected by the cosmic radiation, as well as this space weather aspect, right? With human health and safety and technology health and safety, actually, ultimately on the moon. But there's a number of other planetary studies that can be done, right? The other 2 missions that were selected are not at all like ours. They're looking at optical and thermal imaging of the moon. And I think the big thing with this new program is just the frequency at which these opportunities are arising. And that is unprecedented and super exciting from a scientific perspective. Yeah.
You're listening to Are We There Yet? From Central Florida Public Media. I'm Brendan Byrne. We're speaking with Drew Turner. He's a research scientist at the Applied Physics Laboratory about the Selene mission, which will soon be heading to the moon. Drew, when this does fly, what is the timeline for you getting your hands on this data and observation that Selene will make?
Yeah, that's a fun question. And it's one that, for me at least, it's a completely new regime to be working in, which is such a rapid turnaround and very fast, short lifetime mission. I'm used to working on bigger, longer lasting NASA missions. And with Selene, we're going up. The lander will bring us to the lunar surface. We will start operations shortly after landing, but then we are guaranteed 2 weeks or less of time.
Oh, wow.
Because it's 1 lunar day, right? Moon's orbiting around Earth at an orbital period of about 27 days. And the lunar day lasts for half of that time, right? We cannot yet, or we're not guaranteed, I should say, with this opportunity to be able to survive lunar night, which gets extremely cold when the electronics fail, right? And we're not putting any survival heaters or anything onto Selene. So our mission and our science with Selene is designed to be done within that 2-week span, right? We go up regardless of when that is in time, when that is in the solar cycle. And ultimately, we can actually do our science with 1 hour of data. We'll be able to close our mission criteria and our success criteria with 1 hour of data. Everything else is gravy and bonus in terms of the statistics that we can build up, plus the chances of being hit by something from the sun, right? We've done our baseline so that we're just using the cosmic radiation that's going to be there all the time. If we get a solar energetic particle event with solar cosmic rays, that'll be even better, right? That'll be fantastic for us as well, but we don't need it, the key thing. But ultimately, yeah, so we get 2 weeks or less of operations where we're collecting our data. Data will be streamed back to us very rapidly with very low latency. And we'll be doing the data processing here at APL and providing the data set openly to the public within a short period of time. I'm talking just a matter of a few weeks kind of thing. So that not only will we be able to do the science with the data set that we want to do, right, and that we propose to do on the science team, but then also the rest of the world will have access to it and be able to do what we want to.
I always knew that it was a power constraint, right, because of the solar power and all that stuff. I didn't realize that it was temperature as well. So
Yes.
Selene is going to essentially freeze.
Yes, exactly.
This lunar day.
And that happens. I mean, that's this is a known challenge of lunar operations. Is no matter what, you're going to get this 2-week window where you're in sunlight. If you land right at sunrise, basically, right, you get a 2-week window of sunlight, and then all of a sudden you go into this very cold, very dark environment of lunar night. You don't have solar power, right? So your solar arrays are gone, and you have extremely cold temperatures. I'm talking just a few Kelvin, right? Just a few degrees above absolute zero, because you're airless body looking at deep space.
Mm-hmm.
Yeah.
Terrifying.
It's a tough environment for sure.
Finally, Drew, you mentioned that this work, it's not only going to help, our future of living, working on the moon. It's going to help solidify the models that you've got going now. But could what you learn from the moon be applied to other planetary bodies, say like Martian exploration or something like that?
Fantastic question. So yes, I wonder if you've read the proposal. Actually,
I haven't.
So one of the main science drivers for Selene is looking at how this cosmic radiation is processing the lunar regolith, or the lunar kind of soil, right? The surface materials on the moon. And looking at that, it's called cosmogenic processing with the cosmic ray kind of energy inputs. Looking at that helps us to understand some of the surface weathering over time, as well as some of the planetary formation processes. We can kind of constrain models on how the moon formed. But this is also true for regolith on other airless bodies. So think about asteroids, right? Think about other moons at other planets, other worlds. And that lack of constraint right now is one of the major barriers in terms of understanding some of these other worlds and how they formed. So with the data we get from Selene, that will actually help inform our understanding of other airless bodies throughout the solar system.
Fascinating stuff. Can't wait to hear what Selene finds. And I hope you'll come back and tell us about the findings.
Brendan, I'd be very happy to. Absolutely.
Drew Turner is a research scientist at the Applied Physics Laboratory. Drew, thank you so much for joining us.
Thanks, Brendan.
That's going to do it for this week's show. If you're not already, be sure to subscribe to the show's podcast feed so you never miss an episode. Subscribe on Apple Podcasts, Spotify, or wherever you get your podcasts. Stay connected with the show. Follow us on social media. You can find us on Instagram and Facebook. We're at AWTYSpace. If you got an idea for a future episode of the show, or you think you might make a great guest, well, reach out to us. Our email is arewethereyet@cfpublic.org. Are We There Yet is a production of Central Florida Public Media. Our intern is Orion Boone. Our producer is Marion Summerall. Editorial guidance comes from LaToya Dennis. Support for Are We There Yet comes from our listeners. Until next week, I'm Brendan Byrne. Thanks for listening.